Welcome back, my dear physicist. We're moving on to a new topic today, the topic of electricity and magnetism. And our first lesson will be electric fields. Now, before we get to electric fields themselves, first we need to define exactly what the electric force is. And to do that, I will provide an example. So think about if you rub a balloon on a sweater. We got Captain's sweater here, and we got a balloon. If you rub that balloon on that sweater, you'll find that after that is done, the balloon and the sweater will attract each other. There will be a mutually attractive force between them. However, if you rubbed two balloons on said sweater and then put the balloons together, you would find there would be a mutually repulsive force between those balloons. And this example gives us a basic sort of definition for our electric force, which is electric force. This is electric force, the repulsive force between these objects and the attractive force. And it's kind of like gravity in that it's a non-contact force. These objects don't need to be in contact, so it's non-contact force. But it's dissimilar to gravity because gravity is only attractive, while our electric force can be attractive or repulsive, as given by the example of the balloon with the sweater, or the two balloons together. Now, gravity, well, these are the properties of our electric force, but gravity is caused by mass. We know that, right? Gravity is, if we look at our law of universal gravitation, it's these masses up here that are the property of matter that cause the force of gravity. So there must be a property of matter that causes this electric force, right? Yes, it is. And we have dubbed this charge as physicists, I gave it away. We have dubbed this property as physicists charge. It is represented by a capital or a lowercase q, depending on what you feel like using today. And that given, we can discover through a few more balloon sweater experiments some more properties of charge. Like if you put a bunch of balloons together over here. These really don't look like balloons, but I don't care. The repulsive force will increase. And if you were to put a balloon on the sweater would no longer possess what we would call a charge, because the repulsive and attractive charges would cancel out. And that gives us our basic properties of a charge. Properties. Now, our good old buddy charge, everything in the universe, possesses it. Kind of like how everything in the universe, because it has mass, possesses gravity, gravitational force. Everything in the universe, because it has charge, possesses an electric force. However, charge, unlike gravity or mass, charge can be positive or negative. You can't have a negative gravity, but you can indeed have a negative charge. Like charges repel, and opposite charges attract, where it comes from the age-old adage, opposites attract. We get that from charges. Charges can add and subtract. So they can add together to create larger charges or subtract to cancel each other out. And finally, the little thing we call the law of conservation of charge is that charges cannot be created or destroyed. Another one of those law of conservation of, you got the law of conservation of energy, the law of conservation of mass, law of conservation of charge. There are quite a few of them. So that one's pretty important right there. You probably want to remember that one. The unit of the charge is the coulomb. Named after the famous physicist Coulomb, who was famous for reasons that we will discuss later. And that's just a capital C. And it's a scalar quantity. Charge has no particular direction. Now, we've studied these charges in larger objects, but if we break down the sweater and the balloon to their most simple components, atoms, well, it makes sense that atoms would have charges too, right? Yeah. So every atom has a charge. As a matter of fact, actually, every atom has no charge. It's neutral. But that's because atoms are made up of smaller things. Protons and neutrons and electrons. Protons are positive. Neutrons are neutral. And electrons, which are super tiny, are negative. Now, but I thought you said that everything in the universe has to have a charge. Well, how come neutron doesn't have a charge? That's because protons and neutrons are actually made up of smaller particles that give them these charges, but we won't really discuss the stuff that makes up them until we get to atomic models and atomic theory and stuff. So for the purposes of electricity, protons and neutrons and electrons are as small as we get. Now, however, the charge of the proton and the electron are in fact the smallest possible charges that can exist in matter. And this is dubbed the fundamental charge, which is labeled with a little e there. And the fundamental charge in an electron, or in a proton, an electron it's negative, in a proton it's positive, is 1.6 times 10 to the negative 19 coulombs. That's your fundamental charge. You're going to want to remember that. And another thing, the model of the atom, all the protons and the neutrons are in the nucleus, right? While the electrons float around what we used to assume were orbits, but now we think are more like a general cloud of where it possibly could be. But the important thing is that the electrons are on the outside, which means that they're easy to transfer. So the whole reason that the electric force exists between the sweater and the balloon is because when you rub them together, a lot of the electrons decided to jump ship over to the balloon. The balloon, because it has more electrons than protons now, gained a negative charge, while the sweater, having more protons than electrons, gained a positive charge, which is why they attracted. And because you rub two balloons against the sweater, both the balloons were negative, which is why they repelled each other. And that's the basic idea behind the electric force. Now we get to move on to electric fields. Yay, the whole topic of this lesson. Well, an electric field, just like gravity, because the electric force is a non-contact force, we come up with electric fields. So you have a positive charge here, and a positive charge all the way up here, which is experiencing the electric force. Well, if the electric force is F, and the charge of your larger body is Q, and then the electric field strength, given by capital E, would be F over Q. It's measured, of course, in newtons per coulomb. And that is your electric field strength. Well, it's actually not the Q, sorry. It's not the Q of the larger object, it's the Q of the smaller object. So if you had a little charge of charge positive Q placed in a certain, wherever, in the electric field, and the electric field strength is E, it would experience a force EQ away from this positive orb. If it was negative Q, then it would experience a force EQ towards this positive orb. That's the whole idea behind electric field strength there. It's just like gravitational field strength, except it can be both attractive and repulsive. And, of course, because it's like gravity, we must have field lines. There are field lines because having force, a vector, in its equation, electric field strength is also a vector. Now, you'll notice that for this positive charge I'm drawing, all the electric field lines point away from it. Why is that? Because when we're talking about measuring the general strength of electric fields, we always use a test charge of a positive value. And any test charge of a positive value is going to be pushed away, right? However, if you have a negative charged object, the field lines are always going to be towards the object because any positive charge will be attracted to it. And that's a pretty simple thing there. The the magnitude of the strength is seen through the density of the lines, and its extent is seen through how long it is. It's pretty simple. If you put a positively charged plate in parallel with a negatively charged plate, you could create a uniform electric field between the two. And that's pretty important. When you have a uniform electric field, you can figure out things, as we'll discuss later, that you wouldn't be able to figure out with your typical type of electric field. But first, let's move on to that thing that our old buddy Coulomb is famous for, Coulomb's law. Now, I've been discussing the field strength and the electric force, but how do we calculate the electric force exactly? Well, that's where good old Coulomb's law is. It bears a shocking resemblance to Newton's universal law of gravitation, which just goes to show how similar the electric and gravitational forces are. The force of electricity is equal to the constant of proportionality multiplied by the product of the charges of whatever the two charges, that you're trying to measure the electric force between, over the distance between them squared. I mean, wow, doesn't that look like Newton's universal law of gravitation? It really does. What's that constant of proportionality? Well, in this case, it's going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared. And the meters squared per Coulomb squared is just to get rid of the extra meter squared added here and the meter squared added here and the Coulomb squared added there. It's a pretty straightforward concept. Now, that constant of proportionality comes from something called permittivity. We can calculate that using the formula 1 over 4 pi epsilon naught. And epsilon naught is the permittivity of a vacuum, because we always study these electric fields in a vacuum. Permittivity of different mediums are different, but we don't really care about that. We only care about the permittivity of a vacuum. If you want to know what that is, just a little fun fact. The permittivity of free space in a vacuum is 8.85 times 10 to the negative 12 Coulomb squared per Newton meters squared. But that's just like an extra little tidbit. You don't really need to know that. It's not really a need-to-know basis there. So now let's talk about energy, because we had to talk about energy at some point when it comes to electric fields. You know that by virtue of position in a gravitational field, an object will gain energy. It'll have the gravitational potential energy. Well, the concept is the same when we're talking about electric fields. Let's say you have a big fat positive charge here, and you've got a little tiny positive charge here, and you're trying to push it towards the bigger positive charge. You're going to experience some resistance because of the force of repulsion between those two. So you're going to have to do work on that object to get it closer and closer to the charge. So the potential energy, the electric potential energy, of this charge is defined as the work done to push it from infinity, which infinity, we say infinity because we say infinity, an infinite distance from this charge, is where the charge would not be experiencing any force of repulsion or attraction to it, from infinity to its current position. However, because of, it's just kind of inconvenient to talk about potential energy, electric potential energy, in this sort of way when we're talking about electric charges. So, physicists have come up with another term, potential. Now, the electric potential is the amount of work done per unit of charge to bring the charge from infinity to its position. Right? Right. And so the unit of potential is the volt, named after Alessandro Volta, creator of the voltaic cell, which is important for reasons we once again will discuss later. And the symbol for the volt is V, of course, but the volt is also known as the joule per coulomb. It's joules per coulomb, which means that the formula for our dear potential, or V, as we often symbolize it, yes, we symbolize potential with both V, and the volt is also V, just makes things convenient, would be the potential energy, the electric potential energy, over charge. So therefore, we can calculate our electrical potential energy using the potential times the charge. One problem here. We can't exactly calculate the single potential of one single charge. It's kind of difficult. So what we do instead is we use something called potential difference, whose symbol is PD. And we will be talking a heck of a lot about potential difference. Potential difference is kind of important because what that basically is if you have a charge here that's positive, charge here that's positive, let's say this one's got a heck of a lot of protons in it. And this one's got not so many protons in it. You've got a little test charge here. This one has a potential, and this one has a potential. This one, because it has more positive charges, has a larger potential because it's going to take more work per unit of charge, more charges here, to get this closer to this. This one, it's going to take less work per unit of charge. So now we have a P1 and P2. P1 is greater than P2, and the potential difference is simply P1 minus P2. And you get the potential difference, which is, of course, also measured in volts. And the potential difference is most often used because when we talk about cells. We talk about cells a lot. Now, potential difference can also be used to calculate the fun electric field strength. If you're talking about a uniform electric field, which we talked about earlier when we're talking about two plates of opposite charge lined up next to each other. If you will, consider for a second moving a charge from plate 1 to plate 2, right? You moved it all the way down there. Now, let's just consider, to make things simple, the bottom plate has a potential of 0 volts and the top one has a potential of 1 volt. That makes the potential difference 1 volt. So if the field strength is E and the field strength is uniform, the amount of force required to move from here to here would be EQ, because we know that the electric field strength is equal to the force over the charge. So just multiply, you get force equals EQ, right? Right. And so the force is EQ, and we know, according to the law of conservation of energy, that the work done to transfer this from here to here will be equal to the potential energy that it gained, and the potential energy that it gained is equal, as we determined over here, to the potential multiplied by the charge. And because we already equated that to the work done, we already know that the work done, we know that the formula for work is force times distance, and we know the force is EQ. So EQ times the distance it was moved. And using that definition, we can calculate that electric field strength, as well as equaling force over charge, can be equated to potential over distance when we're talking about potential in a uniform field. So that's just a convenient little formula for potential in a uniform field. One last thing to discuss before we end this video, and that is the electron volt. Now, when we're talking about energy in terms of tiny little electrons, it's really inconvenient because electrons have incredibly small amount of energies when they're moved, because they're moved incredibly small distances. So instead we use a term called the electron volt for charges, and that is simply defined as the energy gained by an electron as it's moved or accelerated, so there's a force pushing it through a potential difference of 1 volt. So if we say the potential difference between P1 and P2 here is 1 volt, it would be an electron accelerated from over here all the way over there. And that is approximately equal to 1.6 times 10 to the negative 19 joules. Which you can see why would it be easier to use electron volts, because that is an incredibly small number. And if that's just 1 electron volt, well, it's a lot easier to use 1 than 1.6 times 10 to the negative 19th. And it's especially convenient if we talk about this example where the electric field is uniform, because then the amount of electron volts will actually equal the voltage of the potential difference. So it's just kind of very convenient. And that is all for this episode. Join us next time where we'll talk about our buddy's charges as they move. It's called a current, folks.